Welcome back. Since lessons 11 and 12 go together very well, we're going to discuss them together here. You were introduced to the quantum mechanical model of the atom. You know that there's no one scientist who can claim responsibility for creating this current model of the atom that we go with. It was the cooperative efforts of quite a number of scientists over a few years. One of those scientists, Niels Bohr, studied light and how electrons interact with the environment. And we're going to pretend that this is the nucleus. Remember, I'm not an artist. And here is an electron orbiting close to the nucleus. What Niels Bohr discovered was that when you apply energy to a reaction, that energy is actually applied to the atoms involved, and specifically to the electrons in those atoms. When electrons absorb energy, it makes them jump farther away from the nucleus. There are different specific locations from the nucleus that electrons can jump to. When they do this, they excite. That is what we call it, when they absorb energy. Now, they actually prefer to be in what's called their ground state. The ground state is their lowest possible energy. All matter actually prefers to be in its ground state. So as soon as possible, the electrons de-excite, which is of course the opposite of excite, and they jump back down as close to the nucleus as they can. When they de-excite, they release that energy in the form of light. Each element has its own unique light wavelengths, which are associated with the energy released by the electrons at the various distances that they can be from the nucleus. Those wavelengths are like a fingerprint for elements, and you can identify an element that is releasing energy based on the various specific light waves. And remember that light is not just visible light, but everything in the electromagnetic spectrum, everything from gamma rays and X-rays and UV light to visible light, radar, microwaves, TV, radio. Those waves can be anywhere in that range. Okay, so when electrons jump, you know that all of the information that the different scientists put together have led us to understand that they live in regions around the nucleus known as orbitals. These orbitals are cloud-like regions, and in those cloud-like regions a pair of electrons can live in each orbital. Each orbital requires a certain amount of energy. The electrons have to have a certain amount of energy to live in that orbital. And the farther away that you get from the nucleus, that energy requirement increases. Now, orbitals are divided into different energy levels. And we are going to talk about those different energy levels here. The energy level closest to the nucleus is called energy level 1. And you're going to find it as a spherical shape. Now this obviously is just a circle, but you need to imagine it as a 3D shape like a ball that goes around the nucleus. Energy level 1 contains an orbital that is known as an s orbital. That s orbital is the spherical shape that I'm referring to. And as we said before, each orbital can hold 2 electrons. You remember that they're spinning in opposite directions from your reading of the text. So this s orbital on the first energy level can contain those 2 electrons. Now, as you add more electrons, they obviously need more orbitals to live in, since each can only contain 2 electrons. So we're going to go up an energy level to energy level 2. That's going to be a little farther from the nucleus. There's going to be another s orbital, which can hold 2 more electrons. There is also going to be a p orbital, which is dumbbell shaped. Those begin on the second energy level. There are a total of 3 p orbitals per level, meaning they can hold a total of 6 electrons. So on that second energy level over here, we are going to add 3 p orbitals. You can imagine that that's a dumbbell shape. And that each of those p orbitals can hold 2 electrons. So we can place a total of 8 then in that second energy level. 2 in the s orbital, 6 in the p orbitals, total of 8. Now that's as much room as exists on the second energy level. If an atom has more than 8, 9, 10 electrons that need to be placed, it needs to go ahead and have those electrons move farther out into a third energy level, where there will be another s orbital and another set of 3 p orbitals, each of which hold their pair of electrons. The third energy level also contains what's called a d orbital. That begins, that's a complicated shape, by the way, so we're not going to exactly talk about what the shape is. The d orbitals, as I said, begin on the third energy level. They require a lot of energy. And there are 5 of them per level, which means they hold 10 electrons. Oops, ran out of space there. There we go. Okay, so we are not going to attempt to draw a d orbital. We're just going to stop and talk about it a little bit, okay? The d orbitals, as I said, require a lot of energy. They require so much energy that the electrons don't jump into them immediately, because the electrons, as you remember, prefer to be in the lowest possible energy state. And s orbitals require quite a bit less energy than d orbitals. So much so that the s orbital up on the 4th energy level requires less energy than the d orbital up on the 3rd energy level. So that 4th energy level s orbital is going to get the next 2 electrons. Then the next 10 electrons after that will go into the 3rd energy level d orbital, which we're not going to try to draw. And then after that, the next 6 will go back into the 4th energy level, p orbital, and so on and so forth.